Good morning, everyone. My name is Kevin Knopf, National Product Manager for Graybar, and I would like to welcome you to Graybar's G2 Talk presentation on test and measurement solutions for oil and gas applications. This talk is part of a webinar series we offer each month for our industrial customers. We have a great discussion lined up for you today, but before we get started, I'd like to cover a few housekeeping items. First of all, if you were one of the first 50 people who joined in on the presentation, you will receive a coupon for a free cup of coffee, courtesy of Graybar, as a thank you for your time today. Also, at the bottom of your screen, you'll see a box for Q&A. Feel free to submit questions throughout the presentation. We'll address as many questions as time permits at the end of the presentation. Lastly, our G2 Talks are all archived on the graybar.com website, so you'll be able to view the presentation again or recommend it to others. We're happy to team up today with Fluke. As an electrical distributor, Graybar works alongside Fluke to provide industrial-grade products for testing and measurement that help you minimize downtime while increasing safety and efficiency. You can visit graybar.com/industrial to learn more about our industrial solutions. At this time, I'm happy to introduce today's speaker, Joel Hartle. Joel has been with Fluke Corporation for 5 years in various operations, sales, and marketing roles. He is currently a member of Fluke's oil and gas applications team, and prior to joining Fluke, Joel was in the Navy, serving in nuclear submarines. So without further ado, I'd like to turn the presentation over to Joel. Joel, take it away.
Good morning, everyone. So we're going to talk about 3 applications today and then have a Q&A session. The 3 applications were sent out as part of the meeting notice, and they are use and selection of hand pumps and pressure test gauges, field gauge verification for both analog and digital gauges, and then last but not least, calibrating a heart pressure transmitter. After that, we're going to have a short Q&A. One point about the Q&A is if there are a lot of questions or if there are questions that either I can't answer, I'll be happy to get back to people. And then throughout the presentation, you'll see me reference a couple of Fluke application notes. If you download those Fluke application notes, a lot of times they'll go into a lot more detail than this presentation can do in the next 30 minutes, and you probably can find the answers to your questions there. So without further ado, I'm going to get started. So we're going to begin today talking about hand pump selection and use. Primarily, hand pumps are selected based on the pressure that you actually need to generate. Typically, the smallest and lightest will be pneumatic pumps. We see primarily scissor pumps, so I've actually got a picture here on the right of a scissor pump attached to a gauge. We've also started to see more bicycle pumps. So if you think of the things that you actually use to pump up the tires on your bicycle where you sort of go up and down, we actually are starting to see a few of those be used in the field. They seem to work pretty well, so we're actually investigating doing a little bit more with those pumps going forward. If you need to generate more, you can use hydraulic hand pumps. So again, I've got a picture here of a hydraulic hand pump attached to a gauge. And the most important thing to remember about hydraulic pumps is that the fluid that you use in those pumps makes a huge difference. Pretty much all manufacturers will recommend that you use deionized or water or mineral oil. If you use tap water, you are going to be unhappy because what will end up happening is the tap water will give you deposits, and eventually your pump won't prime and you won't be able to use the pump until you clean it. And cleaning it is absolutely no fun. You only have to do it once or twice, and you'll remember to never use tap water again. So they've got some nice advantages, which I talk about here. You know, they're portable and lightweight. And you don't need to charge them the way you would with, say, a nitrogen bottle. But as we talked about, you do have to prime them. They are a little bit slower, and you're going to have to clean the unit after you finish pretty frequently, especially if you're applying it in a dry gas environment, say natural gas. Even if you use DI water, you really should clean the unit under test. Couple other solutions I've listed here. One of the most common ones we see in oil and gas is because guys are taking remote trucks to either corners of the site or they are driving out to a remote field location. A lot of guys will have a nitrogen bottle in the back of their truck attached to a regulator. Works pretty well up to 2,000 psi depending on how recently your bottle's been charged, but it can, if your bottle is low, you might not be able to generate enough pressure to do your test. Last but not least, manufacturers are starting to release electric pumps, and so I've actually got a picture of a Fluke unit here that has an electric pump built in. These are primarily the most useful at low pressures. So the unit here, for example, goes up to 300 psi. There are much more expensive units that go up to as high as 10,000 psi. So they're starting to become a useful replacement because pumping is no fun. So let's talk a little bit about gauges. Primarily around gauge selection, pretty much most people at this point in time are using digital gauges. They have become very, very rugged. They're very, very tough and very, very accurate. So most of the time you see people, at least for new purchases or new projects, are using digital gauges. And this discussion is generically true, but I'm going to primarily focus on digital gauges. So the sort of blanket statement here that gauges are most accurate in the upper part of their range is true regardless of how the manufacturer specifies it. We're going to talk a little bit about the specifications and why they matter. You're going to see two main specifications from gauge manufacturers. Either percent full scale, which is a holdover from the analog days. Analog gauges were specified as percent full scale. But you're also starting to see percent reading. So a manufacturer might specify their gauges as a error as a percent of the reading they're giving. So when you talk about full scale specifications, it's critical that you pick a gauge whose upper range is almost identical to where you're going to be working at. So that is if you're going to be working at 1500 psi most of the time, you want a gauge that's as close to 1500 psi as you can. So you'd either want a 1500 psi gauge or maybe a 2000 psi gauge if you can't get a 1500. And if you have a wide variety of working loads, so let's say you spend some of your time at 1500 psi and some of your time at 300 psi, you might want to go out and buy a 500 psi gauge and a 2000 psi gauge to cover the loads. Because what ends up happening is that the lower the pressure is as a percentage of the full scale, you end up with a much higher error. And so I've got the example here on the page that talks about how a 500 psi gauge gives a fairly substantial error at 5 psi. So it actually will give you 5% error, even if it has a very accurate 0.05% error spec. So one of the reasons manufacturers have gone to percent readings is that it allows you to sort of ignore some of these in the lower end. The problem is that at the end of the day, the sensors simply become less accurate the further away you get from the maximum end of the range. And so what will end up happening is that most manufacturers who specify as percent reading will set a floor spec that sets somewhere between 0 and 20%, and it basically says even if you have a lower reading than this, your total error will be fairly high. And so good practice suggests that if you're using a gauge at less than 20% of its full scale, it's probably not the right thing. You probably need to go get another gauge. So here's a graphical representation of that same discussion. These are two actual gauges made by two different manufacturers, and I'm not going to go into who's got what because this isn't a product comparison. It's designed to show that this concept is how this concept works. So you can see the yellow line is gauge A, and gauge A is specified as percent of full scale, and gauge B is specified as a floor as a percent of reading. And what's interesting about this discussion is that I happen to know that these two gauges use the exact same internal sensors. And so this is simply a choice of how the manufacturers chose to specify them differently. And you'll notice that right at 1000 psi or 50% of the range, they cross in terms of accuracy. If you're below that, the gauge B is better, and if you're above that, gauge A is better. And based on the discussion we just had, if you're actually following recommendations, it tends to be that the percent full scale gauge will actually give you better accuracy if you're using the gauges in the upper half of the range, which is pretty much the recommended way to go. And so that sort of discussion around that specification is something that we see a lot, and people will say, well, this one's percent full scale and this one's percent reading. How do I know which one is better? And so the thing you need to know is that the closer you are to the higher end of the range, the better the full scale gauge is going to perform, and the closer you are to 0, the better the percent reading gauge will perform. So last, before we move on to the next topic, I'd like to talk a little bit about four main factors that affect uncertainty. And we're going to get into this a little bit more in the next section when we talk about gauge verification. But I want to introduce the concept here. And so there are four main factors that will affect the uncertainty of your gauge. Time, temperature, whether it's an absolute versus a relative uncertainty, and what the manufacturer's confidence interval. The easiest one is probably time. We all know that gauges tend to drift over time, and so most manufacturers, when they publish their spec, it's only valid out for 1 year. Beyond 1 year, if you haven't calibrated your gauge, the manufacturer won't say that it's within a certain error range. And so if you're not getting your gauges calibrated yearly, you don't really know what accuracy you have. One of the things that you'll start to see is that a lot of the highest quality manufacturers are starting to quote 6-month specifications. So if you shorten the amount of time between when a gauge is calibrated and the next time it's calibrated, you can actually tighten the specification. And so some manufacturers have started quoting 6-month specifications on their gauges for the most high accuracy applications. So people in custody transfer are using these kinds of specifications increasingly in order to reduce their error. Temperature is a factor. I'm hoping most of you have heard of temperature correction. I'm not going to go into a ton of detail about it here, but basically gauges are specified around 23 degrees Celsius, plus or minus either 5 or 3, depending on the manufacturer. And then once you get outside that range, you have to apply a temperature correction. That temperature correction can be pretty significant, and especially in oil and gas, where we see people using gauges in extreme weather, so up on the North Slope or down in the Gulf, where the temperature can get pretty hot. The temperature correction is a non-trivial factor and really needs to be accounted for. I have a bunch of detailed calculations in the application note that I've listed here at the bottom of the page. Absolute versus relative. A lot of times manufacturers will quote a relative spec. That is, it does not include the equipment that was used to calibrate the gauges. That equipment has uncertainty itself. And basically what happens is whenever you calibrate a gauge, the equipment used to calibrate the gauge is calibrated by something else. And that's calibrated by something else. And it goes all the way back to the National Institutes of Standard and Technology, or NIST. And they have the sort of the standard, they'll tell you hey, here's what a PSI is. And so basically, unless you add all of those uncertainties together, you have a relative uncertainty. And so the absolute uncertainty, which some manufacturers quote, will actually give you the error of the equipment used to calibrate all the way through the chain. And that can be very, very useful because you know that the equipment was probably calibrated by the highest quality gauges and other equipment to get it the most accurate. The last and sort of the hardest to talk about is confidence interval. This is something that each manufacturer decides, and most manufacturers don't publish, so it can be very difficult. Usually if you ask the manufacturer, they'll tell you. And basically what this says is that after the quoted time, so 6 months, a year, or 1 year, what proportion of their population will give a reading that is out of specification? And so the key thing here is it applies to a population. So most instruments will be much tighter than this, and most instruments tend to fall on a bell curve like I've got here. And so if one manufacturer uses a 95% confidence interval, that would be vendor X, and the other uses a 99% confidence interval, they will actually quote different specifications even if the performance is identical. So you can see that they are both on this curve, and vendor X here is quoting a 0.019% error, while vendor Y is quoting an 0.025% error because they are using a difference confidence interval. Just to sort of save you the trouble of having to ask us, Fluke uses the more conservative 99% confidence interval. Now, the key thing to remember, and this is why I've got this 68% shaded here, the key thing to remember about this is that the vast majority of instruments will usually be about 3 times more accurate than the stated interval. So it'll be about 68%. So if the manufacturer spec is 0.025, probably 68% of those instruments will fall within 0.08. So that's one way you can get more accurate measures. And we'll talk more about this in the next section. Again, the details are all in this application note, Understanding Specifications for Process Calibrators. It goes into excruciating detail if you want to know more. Last but not least, we'll talk a little bit about the tech tips here. This is sort of a wall of text. A lot of this is common sense, but the reason it keeps being repeated is that it isn't that common. Test and debug your setup before going into the field. Keep your hoses as few as possible and as few connections as possible. If you can, test your pump carefully or mount your gauge on the pump in the shop. Don't try to do it in the field where conditions are not ideal. Follow the priming procedures. I've already said it once. I will say it again before the end of this presentation, but using the wrong fluid is very bad and will cause you a lot more work than you need to. As far as fitting and hoses, we find that a lot of the no tools required, like Ralstons, work really, really well. We really like them. And if you don't have those fittings available or your office won't pay for them, make sure you have all of the things you're going to need: adapters, wrenches, sealing tape. And one thing we don't recommend you use is to use push-fit hoses, because they will eventually leak, and you always end up cutting them, and it changes your system every time you do it, and it's going to mess with your repeatability horribly. Just don't do it. Go out and spend the money and either get the adapters and wrenches, or go out and buy the no tools required fittings. One thing that we see a lot of new guys do is they don't adjust their vernier prior to actually pumping up to pressure. So make sure you take your vernier all the way down, and then as you pump up, stop a little short and use your vernier to ease up to the pressure you need in order to hit your point. Finally, thermodynamic effect. This is primarily for hydraulic pumps. Basically, everyone, when you compress a gas or a liquid, it basically will cause it to heat up. And then once the pressure has met, the fluid is expanded, but then it'll start to cool, right? Because you've added heat to the system, and then the heat starts to escape. And when the heat leaves, basically that causes the pressure to drop. And so when you're using hydraulic pumps especially, you really need to make sure that you leave the system alone for as long as 5 minutes, or potentially more, in order to make sure that the thermodynamic effect gets rid of. And then you basically can adjust it back with your vernier. Then you have the point. This is one reason why hydraulic pumps can be a little bit slower. Okay. Moving on, we're going to go talk about gauge verification. At a high level, the gauge verification procedure, we talked about why gauges drift already, and so I'm not going to recover that, but they can be verified both in the bench or in the field. Benches give you some advantages like really high accuracy. You can use more accurate equipment because you're at a bench. It's also usually pretty easy to clean. In the field, the two main advantages is it's probably a little bit faster because you don't have to take the gauge out, and also it doesn't require you to remove the gauge from service, which can be a real problem if you have an explosive gas in there, say methane, and you don't want to just cap the system off, or maybe you can't. Maybe your procedures won't let you. Sometimes if you're troubleshooting, it allows you to troubleshoot in the environment, which is really useful. So looking at the testing process is pretty straightforward. You basically isolate it. You connect the gauge to whatever you're going to use as a calibration reference. So I've got pictures here of a Fluke 754, but I've seen very, very accurate gauges be used to calibrate gauges. As long as you have enough test uncertainty ratio, that's okay. And then we talked about letting the system sit, especially for higher pressures, and then you basically do a comparison. So the procedure is pretty simple. One thing I'd like to point out here in this picture on the lower left, and the difference between the diagram on the right and the picture on the left, is in the lower left, you see that the pressure module, or the reference gauge, is directly attached to the pump, unlike the way it's set up here in the diagram. This setup on the left is far superior. There's less piping, there are fewer connections, there's less chances for leaks. The simpler you can make your test setups, the better your results will be. All right. So again, this is a fairly simple procedure, so I'm not going to spend a ton of time on it. But the technician tips, one of the things we see a lot of is people don't necessarily, they'll have one rig that they set up in their truck, and they may or may not have actually looked at the fittings and tubing are rated properly. If you're going to be using high pressure, so anything over, say, 500 pounds, you really, really, really need to make sure that it's safe. So guys in midstream frequently will top out at 2,000. Guys in upstream can go up to 30,000. We've seen fracking rigs that easily touch 30,000 pounds offshore. We see it 20,000 pounds sometimes, although 15,000 is more common. And then downstream, it's all over the place, but it tends to be lower pressures, less than 2,000. But there are definitely exceptions. We see more. So make sure that when you do set your rig up, whatever you're going to be testing, make sure that whatever pressure you plan to put through it is rated. Because a lot of times people will forget that, hey, this is a 2,000-pound rig, and they try to put 5,000 pounds of pressure through it, and it doesn't go well for them. It's a great way to end up in the hospital. We talked a little bit about matching the test range's equipment before. So basically, if you're working at 1,500 pounds, try to get a test calibrator or a gauge or whatever you're going to use to be as close to 1,500 pounds as possible. That'll give you the best accuracy. Analog gauges, this is a big difference between analog and digital. Analog gauge, you got to tap a couple of times because you got those mechanical parts that need to move. You've got a little bit of hysteresis error, friction and other forms that cause the gauge to stick, and you just got to give it that little tap in order to clear that. We see that people use nitrogen a lot for gauge verification, especially if they're in a bench, because they're right there and it's really easy to recharge your bottle when you get low. It's not a good idea to use it above 2,000 pounds. It's really, really high pressure gas is not a safe thing to be around. We see a lot of this kind of familiarity breeds contempt a little bit with high pressure and instrumentation techs. And so we'd really like to kind of emphasize that that's just not good practice. Lower volume ways of getting to high pressure, like hydraulic pumps, are probably the better way to go. If you are going to take a bench out of the field, make sure when you calibrate it at the bench, make sure that it's at the same orientation as it will be in the field. This is especially true for mechanical gauges, but it's also true for digital gauges. Placing it at the right orientation will help make sure that you are reducing as many error factors as you possibly can. We talk a little bit about liquid separators. That's very true in hydraulic applications, depending on what your process fluid is. If it has very high accuracy requirements, it has very high purity requirements. A liquid-to-liquid separator will really help. Most manufacturers will sell liquid-to-liquid separators to keep stuff out. And then the last part we're going to talk about here is the accuracy of the calibration standard. And so when you verify things like gauges or transmitters or any other piece of pressure equipment, how accurate does your calibrator need to be? And traditionally, a long time ago, it was as high as 10 to 1. Your calibrator needed to be 10 times more accurate than the unit that was under test. Well, what's happened over time is that the units that we're testing have gotten both more accurate and they are less likely to drift or break. And so those requirements have been relaxed, and current best practice is about 4 to 1. However, that's not all that possible necessarily in the field. Frequently, we'll see guys out in the field calibrating at 2 to 1 or 3 to 1, and sometimes they can't even get that. And at that point, you have to start to wonder, is it really worth doing the calibration? And so people will say, well, we can't calibrate it if we're at 2 to 1. Well, that's not entirely true. Basically, what happens is that when you have a lower test uncertainty ratio, a TUR of, say, 3 to 1 or 2 to 1, what that means is that when you get an out-of-tolerance reading, it means that you have less confidence that it's really out of tolerance. And so frequently, the best way to deal with that is to use a different setup and have someone else try to do the calibration. If you do 2 calibrations with, say, 2 to or 3 to 1 with different setups and they're both out of tolerance, it's more likely that the unit is actually out of tolerance rather than you just had a bad calibration. So that's one way of dealing with it. Accuracy is, so I've got this bottom line here. Accuracy is a good thing, but the real thing that you need is that you need sufficient test uncertainty ratio. And so let's look at a practical example. And so I'm going to bring up this graph. This is a little hard to read, but what you're looking at are the 4 test ranges of a Rosemount 3051. You are looking at 2 calibrators made by 2 different manufacturers, A and B. And again, they have different methods of specification. Calibrator B is specified as percent of full scale. Calibrator A is specified as percent full scale. Calibrator B is specified as percent reading. And what you'll see here is that the low parts of the range, Calibrator B is very, very good and has sufficient TUR all by itself to maintain a 4-to-1 ratio. But as it gets to the higher end of the range, as it gets lower and lower, and in a few particularly bad cases, it gets below 2-to-1. Whereas the ones specified as percent of full scale is more consistent. And what this means is that if your calibrator is specified as percent full scale, it means that you have more consistent performance across the range. Whereas if your calibrator is specified as percent reading, you have to be very aware of whether you're high in the range or low in the range. And if you get an out of tolerance reading, does that mean that the unit is actually out of tolerance, or does that just mean that I don't have sufficient margin in order to be doing this calibration? And so it's very, very difficult to do that. This is getting harder and harder for the manufacturers to get up and improve as companies like Rosemount or Yokogawa build better and better transmitters. And as the process gauges from people like Emerson get better and better, it gets harder and harder to get sufficient margin. And so this is where we start to talk about things like guard banding and other stuff. I'm not going to go into a lot of detail on the guard banding. If you have questions about it, I'm happy to answer it. We have a bunch of really good white papers on that. So basically now we're going to talk about the Hart transmitter calibration. This is actually a fairly simple procedure. I'm going to speak specifically about the 754 because each manufacturer is different. So this is for those of you who probably own a 754 and want to learn how to calibrate it. Some of these are fairly basic, but again, there's an app note that I reference here that you guys can download that will give you a bunch of really good data on this. So the first thing you have to do is isolate the transmitter and the wiring. If you're going across the test diode, as it says, you have to leave the wires intact, but you don't get a great milliamps accuracy there, so it's probably not the recommended method. You have to connect the measurement jacks as shown in the diagram and connect the pressure module cables. Again, like we saw in the previous slide, connecting the pressure module directly to the pump will give you the best results. You don't need a 250 ohm resistor. 754 has it built in. And then last but not least, you have to connect the test hoses. Okay, the process is pretty straightforward. You're going to turn on the calibrator. You're going to turn on loop power. You're going to press the Hart button to see the configuration of the transmitter. I've got a picture of what that looks like right here. So that's the 10.793 milliamps, 901.2 millibar. Basically, at this point, you're going to vent the unit, and then you are going to press the Hart soft key again, and the unit, the 754, should give you the proper combination. You'll hit enter to select, and then at that point you'll hit enter again to hit a linear instrument, transmitter calibration. If it's set for square root output, you'll have to use the square root instrument button, and then at that point you can hit manual test, and it'll begin calibration. At that point, you basically will apply the input pressure. So whether you're using a pneumatic, a gas, or a hydraulic pump, you'll go to the first test point. And at that point, you'll basically, once you get there, you hit the accept, and then you do that for each point on the test. So if you're doing a 5 up, 5 down, you'll do 5 points up and then 5 points down. And then basically you'll measure, if the measured signals are within tolerance, you're done. You basically have done an as found test. pretty straightforward. If you have errors, at that point you need to do adjustments. I'm not going to talk a lot. I've got an example of 3 here that are out of tolerance, and so you see they're all highlighted. All 3 points are highlighted here. And you can actually go back, do the adjustment on the trims, whether it be on the input or the output side, and be done. Again, we have a detailed application note that we've just revised, so this has the latest and greatest information that you can get far more detail on. Since I'm running out of time, I'm going to skip this. Last but not least, we're going to talk about the test tips. One of the things we find is that a lot of times it's necessary to trim the input sensor more than once. Just depends on how long it's been since the unit's been calibrated and what kind of outputs you get. If you see, like you saw there, where everything is out of tolerance, that may be a good symbol that you need to go trim the out inputs again. You've got to zero it. If you don't zero the unit, you're going to get strange readings. Things will not work properly. It has to be zeroed. We talked about allowing milliamps and pressure to settle, and then I'm going to repeat it again and again. Debug your test setup in the shop before you go out there. It will save you so much time and aggravation if you're out in the middle of nowhere, or if you're in a far corner of the facility and you've got a test setup that's leaking and you can hear it. That's not where you want to be. You'd much be preferring to do that in the shop. Make sure that you are using the right fluids. I've said it 3 times now in this presentation. It's probably one of the most critical things when using hydraulic pumps. Last but not least, or actually I guess I'm going to talk about these together. So if the full scale value of the transmitter is less than 25% of the full scale value of the module, select a lower pressure module. What that's basically saying is that if you are at the low end of the range, go get a lower end pressure module. If you are using a 754, similar to gauges, you need to have pressure modules that fit the work that you're doing. What we frequently will see is that people will use, a gauge or a pressure module for most of their work, and then maybe use a gauge for something lower down, and then document the calibration manually. If you have to have the documenting feature, you can get another pressure module. And last but not least, if the pass-fail accuracy is set at the limits of the transmitter, if the pass-fail accuracy is set at the limits for the transmitter adjust, the transmitter if the errors are greater than 25% of its limits. What this refers back to is the TUR. Basically, what it's saying is that if you set it at its limits, and you're seeing errors greater than 25% of limits, you probably don't have sufficient TUR to do the adjustment, and by adjusting the transmitter, you're going to end up making the transmitter less accurate than it already was. What you need is to go get a higher accuracy system, so either more accurate pressure modules, or you need to be able to move the limits in order to make that happen. Okay, well, I've managed to talk for 30 minutes. I am just about out of time, and are there any questions?
Thank you, Joel. It was an excellent and very detailed presentation. I really appreciate it on the Graybar side. At this time, we would like to address some of the questions that have been submitted. Again, this is Kevin Knopf with Graybar. And as a reminder to the attendees out there, you can submit a question using the Q&A box at the bottom of your screen. If we don't get to your question, a Graybar representative will be happy to follow up with you after the presentation. Joel, our first question actually comes in from Greg. He asks, could you describe in a little more detail the temperature coefficient and its impact on accuracy and uncertainty?
Sure. So basically, the temperature coefficient is set by the manufacturer, and I'm actually going to go back to that slide if that's okay. Let's see. Let's go backwards. Oops, wrong slide. There we are. Perfect. Okay. And so basically, I've got it set as the function here for TC is equal to X% divided by degree C. And basically what it's saying is that most manufacturers will put their gauges within a certain range, and then as you go out, you have to compensate. And they'll give you a number. X will be a value, 0.0012%, for example. And so for every degree C you fall outside of the temperature compensated range, you have to add an error factor. And so this can get pretty complex. Most manufacturers will say that, hey, this gauge is 23 plus or minus 5, 23 plus or minus 20, 23 plus or minus whatever. And then as soon as you get outside that range, you need to calculate an additional error. And if you're in a high accuracy application and you're trying to do something in the bitter, bitter cold or the extreme heat, you need to think about, well, okay, do I need to compensate for accuracy? If you're doing something simple like setting a limit switch, it might not be necessary. But if you're doing something like calibrating a custody flow transmitter, yeah, you probably need to do it. And we see a lot of guys who skip it, and they can get into a lot of trouble, especially in the extreme cold. If you get down below about minus 20 C, I'm not aware of any manufacturers who are using a sensor who have a solid linear response below 20 C. Negative 20 C. So if you're up in Canada or you're on the North Slope in Alaska or you're in the Bakken and you're, in really, really cold weather, you really need to take steps in order to keep your unit warm. One of the things we've seen that actually works really well is people will use the hand warmers. You can tell that your unit's getting too cold because the LCD will start to freeze. And at that point, you need to get the unit warm again because you're going to start having errors in your response. So the compensation is really designed to handle the less extremes, down to 0, negative 10, or up to 50. And will basically just help you get the most accurate measure you can, or at least tell you how much error you're adding. And you can't always control that. And that might be a decision where you say, hey, this is so high accuracy, I have to have it more accurate. So maybe that's when you take the unit out of commission, remove it from the system, take it back to the shop, and do it at the bench. Does that answer your question?
Absolutely. Thank you, Joel. As a reminder to the audience, you can certainly submit a question using the Q&A box at the bottom of your screen. Joel, our next question comes in from Todd. Does Fluke make regulators?
No, actually we don't, although I'm sure your friends at Graybar will be able to help you find a good regulator. Fluke doesn't make any at this time, though. Thank you. Sure.
Well, at this time, it doesn't appear that we have any additional questions. I know that the presentation that you put together covered a lot of the points, very detailed, and did a great job of hitting all those what might be questions. So I really appreciate the time, Joel. As a reminder for all of those on the call, this presentation will be archived and on the graybar.com website. Again, I want to thank everybody for their time today. And hope you will join us again next month for the Graybar's Industrial G2 Talk. Thank you to everyone.